At 35,000 feet, a jet glides through air thinner than the atmosphere atop Everest. The pilots know their altitude down to the nearest foot. But how? There is no invisible tape measure from ground to sky. The aircraft builds a model of the air around it: pressure, temperature, radar, and physics. It starts with barometric altitude, height inferred from atmospheric pressure. As you climb, pressure drops in a predictable pattern. Static ports feed that pressure to air data computers, turning it into electrical signals. Older planes use aneroid capsules, tiny bellows that flex with pressure and drive the needle. Modern jets use digital pressure transducers, silicon sensors translating microscopic deflection into voltage with extreme precision. That produces pressure altitude, height relative to a standard reference of 1013.25 hectopascals. It is not the height above ground. It is height above an imaginary standard atmosphere. To match reality, pilots set local pressure, QNH, giving indicated altitude. True altitude corrects for pressure and temperature. Your actual height above means sea level. Density altitude is the performance altitude. Thin, hot air hurts lift and engine power. Air data computers merge pressure and temperature, cross-checking multiple sources to spot errors. If a static port is blocked, readings can freeze. The aircraft climbs or descends while the altimeter does not. In Aero Peru 603, taped-over static ports fed false altitude and speed, leading to total confusion and a fatal crash. Modern jets use redundant air data computers, 2 or 3 independent units. They take inputs from static ports for altitude, pitot tubes for airspeed, and temperature probes for corrections. High-accuracy piezoelectric or capacitive sensors convert analog pressure into digital altitude data. The ADCs feed the PFD, the autopilot, the transponder, and the flight management system. If one disagrees, the system isolates it, flags it, and trusts the others. Transponders transmit pressure altitude to air traffic control for separation and alerts. In the Charkhi-Dadri collision, miscommunication and lack of real-time verification allowed a fatal altitude deviation. Pressure altitude is relative to a pressure level, not the ground. Radar altimeters fix that. They send radio waves down, measure the return time, and compute exact height above ground up to about 2,500 feet. Essential for landing, terrain following, and auto-land, when precision must be immediate. Korean Air 801 descended prematurely amid navigation issues, a stark reminder to cross-check barometric and radar altitude. Modern systems constantly compare both to validate absolute and relative height. If sensors fail, inertial reference systems estimate altitude by integrating vertical acceleration over time. GNSS adds geometric altitude, height above the Earth ellipsoid, accurate enough for navigation. The flight management computer fuses all sources to maintain a reliable picture, even when data disagree. Every foot is a calculation: pressure, temperature, radar, and time, checked and rechecked. At 900 kilometers per hour, 100 feet can matter.